everyone, welcome back. In this video, I'll cover lesson 6 work, energy and power of an NIOS board in one shot with the solved examples. Today, we'll cover work done by variable force, power, work and kinetic energy, potential energy and elastic and inelastic collisions. I've added the timeline in description you can use that to find the topics you're looking for. Okay, so what is work? In everyday life, we say work can be studying, groceries, exercising. Okay, these are work. But in physics, what is work? We are speaking about work done when a force causes displacement. Let me explain that. Let us suppose here to this object, there's an object here, a constant force is applied. It moves along the horizontal distance d to here. The work done by a force is the product of magnitude of force component in the direction of displacement and the displacement of this object. So this is the definition. Let us see what that means. Suppose this force is acting along this direction at an angle theta. This is the direction of displacement. So the component of force along this is, we know it is F cos theta. So it's product of magnitude of force component in the direction of the displacement and the displacement of this object. So this is the force component and this is the displacement. We know this is a force is a vector, displacement is a vector, work as F dot D. So here let's conclude some points here. So if there is no displacement, no work is done. Therefore, work is a scalar quantity. You're trying to push the wall, there is no displacement. So basically, there is even though you're exerting the force, there is no work. Let's see what is the unit of work. The unit of work is joule, defined by joule. So seeing work is equal to force into displacement. F dot D. Unit of Newton, force is Newton, displacement in is meter. So Newton meter, we define it as joule. So 1 joule is defined as the work done by the force of 1 unit, and it moves the distance, displacement 1 meter. So this is the definition of joule. You got it. The dimensional formula of work. We saw that work is force into displacement. We know from Newton's law force is equal to mass into acceleration into the displacement. Let us see the dimension. Mass, the dimension of mass is capital M. Acceleration unit is meter per second square. We denote meter dimension as L, second in T. So acceleration's dimension is L T power minus 2. So we write that here. L T power minus 2 into distance is again L. So dimension of work is L square P power minus 2. This is the dimensional formula of work. So let us see the second example. The force of 6 Newton is applied on an object at an angle 60 degree with the horizontal. Calculate the work done in moving the object by 2 meters in the horizontal direction. So this was the object here at an angle 60 degree. We are applying a 6 Newton force. It moves a distance of 2 meters in horizontal direction. What is the work done? We know work done is equal to F cos theta into D. F is 6 Newton. Cos 60 we have to know, and distance is 2 meters. So what is cos 60? Cos 60 is 1 by 2. So cancelling, we get 6 joules. Let us see another example. A person lifts a 5 kg potato from the ground floor to a height of 4 meter to bring it to the first floor. Calculate the work done. Here, this is the object. This is lifted up to a height. This is the height of 4 meter. Mass is 5 kg. From the ground floor to first floor. Calculate the work done. We saw in last previous chapter, we have the gravitational force. So when we move this object up, it is gravitational force acting. What is the force here? M into G. What is the mass? 5. What is the gravity acceleration due to gravity? 9.8 meter per second square. So if you multiply, we get 49 Newton. Now we know the force. Force is in this direction. So work done against gravity is force into displacement. We know that work is scalar, so there's no direction for the work. It's not a vector. It only has magnitude. So we can apply F into D. Distance is 4 meter. 9 fours are 36, 4 fours are 16, 17, 18, 19. So 196 joule is the work done in this case. Till now we saw how to get the magnitude. There is force, there is displacement, and there is work. We missed out on one more component, theta. The angle theta between them is also important. In fact, it leads us to say whether the work is positive or negative. A car is moving. When you accelerate the car, a force F is applied in the same direction. As a result, we increase the speed of the car. So the force and displacement both are same direction. Then theta is 0. So you are applying the force here. The direct displacement is also in the same direction. So theta is 0. Therefore, the work done is F cos theta. Cos 0 is 1. Work is Ft. So in this case, work is positive. And when the same car is moving, and when you apply a brake, a force F is applied in the opposite direction. So you are moving and you apply a force F. When you apply a brake, here both are in opposite direction. So theta is 180 degree. Cos 180 is minus. So work is minus Ft. Therefore, in this case, work is said to be negative. Now let's see about work done by the force of gravity. Suppose this mass m is being lifted to a height h. The weight of this object is mg. The work is done against the force mg, that is, the weight is this, the force is this direction. We are doing the work against the force of gravity. So the displacement is upward, force is downwards. So the angle between the force and displacement is 180 degree. So in this case, work done is Ft cos 180 minus mgh. So when we lift the object, work done is negative. Well, in the case of object falling down, this object is lowered down by the height h. So here also the weight acting downwards is mg. Displacement is also in this direction, height h. So in this case, the mass is being lowered. So the force and displacement are in the same direction. Therefore, theta is 0 degree. Work done is Ft cos 0 positive mgh. So we say the object is lifted up. The work done by the gravitational force is negative. But the work done by the person lifting the object is positive. Let me clear this part. Here we need to see about the interpretation part properly. If you see, if this object is being lifted we are speaking about the force due to lifting, then the direction of force will be this and that, it will be positive. But the object being lifted and we are speaking about the gravitational force, then it is work is negative. So you need to see which force we are speaking about. Till now we saw about the force acting on the object is constant. Now let us consider the situations where the force responsible for the work keeps varying with time. That is, here the magnitude of force from this point to this point, it is same. Now we are considering a situation where the force magnitude is varying. Like if you apply say 10 units, when you move here 20, here move 30, 40, 50, 60, like you are slowly increasing the force. That is what we are going. We'll see what is the work in this kind of situation. So, work done by variable force. The force responsible for doing work may keep varying with time. So, the magnitude of force f of x changes with the position x of the objects. Let's consider this situation. So, here we are going to calculate the work over large number of small intervals of displacement del x. The del x is taken so small that the force f of x can be assumed to be constant over that small interval. And so, the work done will be during the small displacement is del x given by f of x del x. Let's see how. Let me show you how it is done. So what I am saying is, if we plot the graph of this variable force with respect to the position, that is, there is an object here at the position xi, the same surface, we are applying the force f of x, and it say moves to say xf is the final position. Here it's 10 Newton, 20 Newton, 30 Newton, 40, like it's varying with respect to the position. If we plot the graph of f of x, say it's varying like this. This is xi, this is xf. So how we can calculate this forces work done in this kind of situation is, we know for a constant force, work done is F into D. So suppose if we split this into smaller displacements, so let us say this is del x, then in this case the work done is force f of x into del x. This is work done in this small displacement. This is how we got this component del w is equal to f of x into del x. So this f of x del x is numerically equal to this small area. And to calculate the total work done from this point xi to this point xf is sum of all these areas, right? So that is summation of del w, which can be written as summation del w equal to summation f of x into del x. The width is made so small as possible. The area of all the strips added together will be equal to total area enclosed between xi and xf. If this length is so small, this can be further divided. How much ever small you can make it, that small if you divide. Sum of all the area of strips is equal to total area enclosed, and it will give us the total work done by the force between xi and xf as work is equal to del of summation f of x del x limit del x tends to 0. This is the work done by a variable force. Simple example of variable force is the force exerted by a spring. When you pull the spring or push the spring, you think the force is constant? No, it varies with position. Consider the situation where you are pulling the spring. As the position is length is increasing, you have to apply more and more force than the force you apply here. So this is an example of variable force. So in this figure, you can observe three kind of situation. Initially, the spring is at equilibrium position. where one end is attached to the rigid wall and the other end is attached to the block of mass m. We are taking x-axis along this horizontal direction. So we'll say this as the position x equal to 0 as our reference. If we compress the force, in the second situation we are compressing this block. So now the spring is now compressed, and in this case we are elongating the spring. How are we doing this? By an external force. Here the spring is compressed to a distance x, and here the spring is elongated. And the maximum compression or elongation we denoted by xm. This is the highest maximum force or the maximum elongation possible. When we apply an external force, there's one more thing. An internal force Fx comes into the play in the spring due to elastic property. Like if you are compressing it in this direction, the spring will be like, no, I want it to be in equilibrium position. So here there is in this direction there is internal force Fs. This is due to elastic property. So this force Fs keeps increasing with increasing x and becomes equal to F when the compression or elongation is at maximum. Therefore, at the maximum position, F will be equal to Fs. It will be in opposite direction. You might have observed when you elongate, suppose in this condition you see here it was here, the block was here, you are elongating the spring elongating. At say xm, the maximum force, there will come a certain point where you can't pull the spring further, it will break down. That is when the internal force Fs and the external force F will be equal at xm. According to Hooke's law, this force due to spring can be is denoted as Fs is equal to k times x, where this k is known as the spring constant. Like how we found force due to gravity as mg, force due to spring is kx. And since the direction of Fs is always opposite to compression or extension, it is written in negative. So Fs is equal to minus kx. Now let us calculate how the work done by the spring and also examine if it is positive or negative. In compression of spring, the external force F is directed towards the left, and the displacement is also compared to the equilibrium is in the left. Hence the force and displacement are in the same direction. Therefore theta is 0. Then work done is positive in compression. However, for the same direction of displacement, the restoring force Fs or the internal force is towards right, and F and X are here opposite direction, so theta is 180 degree. Hence the work done by spring is negative. So if you observe the same compression force, the work done due to external force is positive, whereas work done due by spring force is negative. So spring is expanded, force is in, you are applying the force in right direction, the displacement is also in the right direction. So the work done by the external force here is positive, whereas this work done by the internal force Fs is opposite to the direction of displacement. So work done by the spring force is negative. So when it comes to work, what you have to be careful is which force we are speaking about. That determines whether the work is positive or negative. Now that we know the positive, whether the work is positive or negative, now let's calculate the magnitude of it. So initially at x equal to 0, when it is at equilibrium, the restoring force or the internal force is also 0. Now as x increases, Fs is also increasing, and it becomes at a certain point equal to the external force F when at the maximum displacement x equal to xm. Here, if you observe, the variation is linear with the displacement. So we can calculate that the average force during compression or extension is, initially the force is 0, finally the force is Fs by 2. This is the average force. It is equal to Fs by 2. So the work done by the force, spring force is given by force into displacement. The force is Fs by 2, displacement is x. So this is the expression for work done. But we know that the magnitude of Fs is k times xm. We are calculated at the maximum position. So the work can be written as half into Fs is k times xm, and the displacement is also xm because that is the point where we are calculating. So we can write the work done as half kxm square. So this is the work done by a spring. See it graphically, the same concept. Force was linear to displacement. In case of compression, the x was negative, so force was increasing at point xm, it was maximum. And similarly, this is the graph when during elongation. You see that the displacement and the force are opposite in magnitude. Anyway, if we can plot the graph, we can calculate the work done easily. It's the area of the shaded triangle. So we know that the area is half into base into height. So what is the base? Base is xm. So we write xm, height is the force kxm. So kxm. With that we get work is equal to half kxm square. So we have proved the work done both theoretically and also graphically. Now let's measure the spring constant K. Suppose there is a spring vertically suspended as shown here. Now we are attaching a block of mass m. Due to gravity, it extends some distance here. We'll measure the extension here. Say it is S. If you notice for some time and leave it like that, this block will extend only to a certain point. It won't extend further. Why does not extend further? This is because at this point, the restoring force Fs is acting upwards, balances the weight mg. So we say F is equal to, so F is kx, and in this condition, the force Fs is equal to mg. So if you equate, we get k is equal to mg by s. This is the spring constant k. Now let us see an example. A mass of 2 kg is attached to a spring. Light spring of force constant k equal to 10 Newton in meter inverse. Calculate the work done by the external force in stretching the spring by 10 centimeter. So there is a spring attached to a mass. Here the mass of it is 2 kg. The spring constant k is 100 Newton meter. Calculate the work done by the external force in stretching the thing. Suppose block is stretched from here to here by 10 centimeter. We have to calculate the work done. We saw for the spring the work done is half kx square. Now k is 100 Newton meter inverse. Distance is 10 centimeter. So 10 centimeter is 10 into 10 to the power minus 2 meter. Therefore, it will be 0.1, right? So 0.1 square. So half is 0.5 into 100 into 0.01 gives us 0.5 joule. This is the work done. we saw this is a work done by external force F. If you are speaking about the work done by internal force or the restoring force Fs, that will be negative. So work done, it's not asked here, but for your clarity, work done by the restoring force will be minus 0.5 joules. Till now we learned how to calculate the work done by a force. We didn't consider whether the work is done in 1 second or in 1 hour. We didn't calculate that with respect to time. But in our daily life, however, the time taken to perform a particular work is important. So you have to see about time. Suppose a man may take several hours to load a truck with cement bags, whereas a machine may do the same work in less time. Therefore, it is important to note the rate at which this work is done. Here comes power. The rate at which work is done is called power. So, mathematically seen, suppose the work is done in time del t. Del w is the work. At t equal to 0, work is w naught. At t equal to 1, w1. So change in work, change in time is denoted by del w and del t. So the average power is defined as the work done by time taken. So P is equal to del w by del t. What if the rate of doing work is not constant? We saw force was varying. What if this work is itself not constant? In such cases, we need instantaneous power. So let us define the instantaneous power as limit t tends to infinity, del w by del t can be written as dw by dt. Now let's see what is the unit. The SI unit of power is watt, which is capital W. Let us define watt. W. The power is 1 watt when 1 joule of work is done in 1 second. We calculate the power in more common units like kilowatt or megawatt. Kilo is 10 power 3 and mega is 10 power 6. Now let us examine or let's determine the dimension of power. We saw power is equal to, we know that work is force into displacement by time. So dimension wise, force is you can split it as mass into acceleration into distance by time. Acceleration's dimension is meter, unit is meter per second. So meter is length, t, so L t power minus 2. So dimension can be written as, this is mass, this is meter. We are saying here I'm speaking about unit, here I'm speaking about the components. So force equal to mass into acceleration. Dimension of mass is m, dimension of acceleration is L into t power minus 2, dimension of distance is L, dimension of t, time is t. So in total it is, dimension of power is m L square t power minus 3. This is the dimension of power. Isn't calculating dimension easy? Before moving on further, we have to see power in kilowatt, because this is what we will be using in electricity terms. We have heard this much kilowatt of power this machine takes, this device takes, washing machine takes this much kilowatt hour. So in electrical measurements, we measure power in kilowatt hour. What is this kilowatt hour? Kilowatt, 1 kilowatt into 1 hour. Kilo is 10 power 3. 1 hour, let's say in discuss. 1 hour is 60 minutes. 1 minute is 60 seconds. So 1 hour is 60 into 60 seconds, which gives us 3600 seconds. So how did this come? Power is equal to work done by time. Unit of work is joule, unit of time is second. So joule, 10 power 3 joules per 1 second into 3600. So which will come out to this. So 3.6 into 10 power 6 joule. 1 kilowatt is 3.6 megajoules. The electrical energy that is consumed in homes is measured in kilowatt hour. In common man's language, 1 kilowatt hour is 1 unit of electrical energy consumption. Now let's move on to energy. We saw work, we saw power. Now let's see energy. Energy, there are two things we'll be seeing: kinetic energy and potential energy. First, let's see work and kinetic energy. The capacity to do work is called energy. Consider a car moving on a road. It uses a chemical energy of fuel, petrol or diesel. Like, it can push an object when it comes to some distance. So there is some work done. All moving objects possess energy because they can do work before they come to rest. And we call this energy as kinetic energy. So kinetic energy is the energy of an object because of its motion. I explain what I said in an example. Consider there is an object of mass m. It is moving along a straight line due to when we apply a force F. Say it moves to a distance S. This is the distance. And the force of magnitude is along the direction of motion. So this contributes to work. Let's keep that work part separate. Now let's speak about this force. This force produces an acceleration because of which the object moved from here to here. So let that acceleration be A. Then from Newton's law, second law, we know force is equal to mass into acceleration. Now, when there is acceleration, that means this object is moving at some certain velocity. Let us say here at this instant the time was t1 and the velocity of this mass is v1. It moved to a distance s, and at this point let's say the time is t2 and it's moving at the velocity v2. Now during this interval between the time t1 minus t2, the object covered a distance s. So from equations of motion, we write v2 square is equal to v1 square plus 2as. So from this we can write a is equal to v2 square this minus v1 square divided by 2s. Substituting for a in this equation, so F is equal to mass into v2 square minus v1 square by 2s. Now we know work is equal to force into distance. We know from this force is equal to m v2 square minus v1 square by 2s into s. If we cancel this s, we get half m v2 square minus v1 square, which is half m v2 square minus half m v1 square. So this is k2 minus k1, the kinetic energy. This is the final kinetic energy, this is the initial kinetic energy. So the k2 minus k1 denotes the change in kinetic energy. Which is equal to the work done by force. So what we saw is kinetic energy is energy of object because of the motion. So here there was a motion of the object. Because of this motion, the energy we derived is the kinetic energy. Now, kinetic energy is a scalar quantity. It depends on just the product of mass and velocity. It does not matter which one of the two is small or which one is large. The total value determines the kinetic energy. Now, this leads us to one more theorem called work energy theorem. It states that the work done by the resultant of all the forces acting on a body is equal to change in kinetic energy of the system. Mathematically, what did we get? Previous derivation we saw half m v2 square minus half m v1 square. This was initial final kinetic energy, this was initial kinetic energy. So the work done by the resultant of all the forces acting on a body is equal to change in kinetic energy of the body. Simple as that. Now let's see an example. A body of mass 10 kg is initially moving with the speed of 4, this is meter per second, 4 meter per second. So this is m, this is initial velocity v1. A force of 30 Newton, this is F, is applied to the body for 2 seconds. So change in time t2 minus t1 is 2 seconds. What is the final speed of the body after 2 seconds? How much work has been done during this period? What is the initial kinetic energy? What is the final kinetic energy? What is the distance covered? So that the work done is equal to change in kinetic energy. So let us find first the final speed of the body after 2 seconds. We know F is equal to ma. Force is 30 Newton, mass is 10. We need to find acceleration. So acceleration is equal to 3 meter per second square. We know V2 is equal to V1 plus AT. From this we can get V1 is 4, A is 3, T is 2. So 3 to 6 plus 4, 10 meter per second. Now we need the distance covered. S is equal to ut plus half at square. So initial velocity is 4, time is 2, half into acceleration is 3, time is 2 square. So this is 3 2s are 6, 8, 8 plus 6, 14 meter. Now next we know work is equal to force into distance. Force is 30, distance is 14. We get 4 3s are 12, so 420 joules. So this is work. Next, initial kinetic energy K1. K1 is equal to half mv1 square. Half into mass is 10, velocity, initial velocity is 4 square. 4 square is 16. 160 by 2 is 80 joules. Then we need final kinetic energy, which is half m v2 square, which is half into 10 into 10 square. This is 5. This is 500 joule. So we find any final velocity, work, kinetic energy final, distance. Then we need to prove work energy theorem. So work is 420 joules. Now change in kinetic energy K2 minus K1 is 500 minus 80, which leads us to 420 joules, which is equal to work. So same as work, so this proves the work energy theorem. Now let us discuss about potential energy, the other kind of energy. So we saw that kinetic energy is due to the moving object. Potential energy is another kind of energy due to their position in space. A familiar example that I can give you is gravitational potential energy possessed by a body in gravitational field. Let's see this potential energy in gravitational field in detail. So consider a mass m. Say it's the height h from the Earth's surface. The person is lifting his mass from the height h1 to the height h2. The force with which the object is to be lifted is against the gravitational field. So if this mass here has a gravitational force mg, then the person is lifting this with the weight the force F is equal to mg, only then the object can be moved from here to here. So the magnitude of force is mg, that is acting downwards, and the distance displaced is h2 minus h1. Then the work done by this person from here to here, the lifting, is F is equal to force into distance. Force is mg by the person, distance is h2 minus h1, which we have named it as h. Now this is the direction of force, this is the distance, same direction, so work is positive, and it is stored in the mass m as energy. Now the energy by virtue of position of space is called gravitational positional energy. That is, if you see here, this was the surface, the mass m was lifted from here to here. When it is here, after it is displaced, that means that it has a capacity to work. Like if you release this object, it will move back here. So because it is some position above the height from the gravitation earth surface, we call this as potential energy. So what I'm saying is, if the mass is left, it will fall down, and during the fall it can make to do the work. So when it is falling, due to the motion, we saw this object here has some kinetic energy. But at the same time, when you after you lifted it up here, because of the position in the space, it has some energy to do work. That energy is called as potential energy. Like if you see, there is a spring here, there is a mass here connected to some stand here, this is having another mass here, so it's like a pulley system. Now what happens when you release this string? This object will come here due to the gravitational force, so and this object will come up. So what we are saying, it can lift another mass if properly connected to a string or a pulley. This mass, to do work, it had some energy, and that energy is potential energy because it is at the height h. Some points you need to consider here. Thus, initial height selection is arbitrary. There's no importance here. The concept here is, you need to know is the change in height, h2 minus h1. We therefore say the point of zero potential energy is arbitrary. We just take it for an example. We initially considered at this side the body object had zero potential energy, and here it is having potential energy. So any point in space can be chosen as point of zero potential energy. Normally we are assuming that the surface of the earth is considered as zero potential energy for our calculation to be made easier. Now let us see an example. A truck is loaded with sugar bag. The total mass of the load and the truck together is 100,000 kg, 10 power 5. The truck moves on a winding path up a mountain, say to a height h. So there was a mountain, here it was, the truck was here, it's rotated. Say it's here now. And this height difference is the height they are speaking, which is 700 meter. Time taken is 1 hour. What average power must the engine produce to lift the material? So we saw that there is a change in height, so there was a potential energy when it is here. So what is the work done due to gravitational field? Potential energy due to gravitational field is mgh, which is 10 power 5. Acceleration due to gravity is 9.8 meter per second, and the height difference is 700. Multiplying this, we get around 68.6 into 10 to the power 7 joule. Now 1 hour is 3600 seconds. We need power. Power is work by average work done by time taken, which is 68.6 into 10 to the power 7 by 3600, which will we get 1.91 into 10 to the power 5 watt. We say the power in terms of engine in horsepower. So you should know here one more thing is 746 watt of power is equal to 1 horsepower. Therefore 1.91 into 10 to the power 5 watts of power in horsepower can be written as, let's say, x equal to 1.91 into 10 power 5 divided by 746, which will be around 256 horsepower. So this is the average power. Let's move on to another example. A hydroelectric power generation uses falling water source as a source of energy to turn the turbine blades and generate an electrical power. In the power station, 1000 into 10 power 3 kilograms of water falls through a height of 51 meter in 1 second. Calculate the work done by the falling water and how much power can be generated under the ideal condition. So initially, at the top of the, if the water is falling here, the potential energy of the water due to the gravitational field will be mgh. So this will be what the work done would be. So mgh is 10 power 6 is the mass, 1000 into 10 power 3. Acceleration due to gravity 9.8. Height is 51 meter. So this will come around 500 into 10 power 6 joules. So all of this potential energy will be converted into work in moving this turbine blade. Therefore, you see, I didn't directly equate it. Work is force into distance. Force was the gravitational force mg, distance was h. So we again come up to the same thing. So the work done is 500 millijoule. Next is how much power can be generated under ideal condition. So power is work done by time taken. It is said this much of work is done in 1 second. So 500 millijoule by 1 second, 500 milliwatt. Here ideal conditions means that there is no loss of energy due to any frictional forces. But that usually in practical case there will be some loss in machine. Such losses can be minimized but never be eliminated. One more potential energy example would be potential energy of springs. Suppose an external force is applied to compress or stretch a given spring. The external force be F. We saw that the spring, suppose it's compressed by, say, a distance x. The work done by the external force to compress the spring, we found it to be half kx square. This work is stored in the elastic potential energy as in the spring. So that means that the internal force that we say, or the elastic force of the spring, that is due to the elastic potential energy. So when we let the spring free, it bounces back and the potential energy of the spring is converted into kinetic energy of the mass. This is what happens, is what we say it comes back to equilibrium position. Next is conservation of energy. We see around us various forms of energy, but we are familiar with some forms more than others, like electrical energy, thermal energy, gravitational energy, chemical energy, nuclear energy, etc. Now, these forms of energy are very close to related. It can be changed from one form to another. And there is a fundamental law about this energy that is called known as law of conservation of energy. It states that the total energy of an isolated system always remains constant. It can only be changed, but the total energy will always be constant. In an isolated system, if there is any loss in one form, there is a gain equally in another form. Thus, energy can be neither be created nor destroyed. One such example could be like the universe is also an isolated system, as there is nothing beyond this. It is therefore said that the total energy of the universe is always constant in spite of variety of changes taking place in the universe every moment. Another example would be considered the thermal power station. Here the chemical energy of the coal is changed into electrical energy, and the electrical energy runs the machine. In these electrical machines, the energy is converted into mechanical energy, light energy, or even thermal energy. So this explains us the law of conservation of energy. Let us see some few examples in depth about this conservation of energy further. Let us now understand the conservation of mechanical energy during the free fall of a body, like how validity of this conservation of energy. Let's prove with this example. Suppose an object of mass m lying on the ground is lifted to a height h. So when it is lifted to height h, at this point, this object has a potential energy due to the gravitational force, which would be mgh. So the work done is mgh is stored as the potential energy in the object. This was the first part. Next, we are making this object fall freely. And say it has fell from this point to a point P, which is of height. The distance covered would be, say, height h. At this point P, the object is at height h2. Now at this point, because of this gravitational force, we say the potential energy at point P would be mg h2. So we saw the potential energy part. Let's see the kinetic energy part. So when we see this part, the object fell from height h1 to h2. Initially at this point, the velocity is 0, and at the point P, the velocity was v. We can calculate the speed when it has fallen from the height h1 using the equation v square is equal to u square plus 2gs. Since u is 0, s is h1, v is equal to 0 plus 2g h1. If you observe, at the point P, the work done due to this motion, there is a kinetic energy at this point P. And this kinetic energy is half mv square, that is kinetic energy at final position, which is half into mass of the object bm, m into, this is 2gh1, right? 2gh square. V square is 2gh. If you calculate, I missed h1. So we get the kinetic energy as mgh1. So total energy at P would be the kinetic energy plus potential energy. Kinetic energy we found to be mgh1, this part. Potential energy at point P was mgh2. If we take mg common, it is h1 plus h2. h1 plus h2 is height h, which is equal to mgh. This is same as the potential energy at the highest spot. Initially, since the u is 0, if you say at this point, the kinetic energy is 0. So the total energy of this object at this point is mgh. Here also it is mgh. So energy is not created nor destroyed. It is conserved. Converted from some part of potential energy got converted into kinetic energy. So the total energy is conserved. Let us see another example. Conservation of mechanical energy for a mass oscillating on a spring. In the figure, you can see that a spring whose one end is connected to a rigid wall and another end is connected to a wooden block. This is a wooden block lying on a smooth horizontal surface. This point is x at a distance x0 from the wall. Consider another block of mass m moving at a speed v along this line. This block moves and it collides with the spring, because of which the spring is compressed to a distance of xm. Let us consider this xm to be the maximum compression to which the spring can be compressed. Now if you observe at x0, the total energy of the spring was only the kinetic energy of the block. So at x0, the total energy was the kinetic energy, which was due to the block half m v square. Extreme compression, the potential energy of the spring. Here the potential energy is 0 because the spring we are speaking about potential energy of spring. The potential energy of the spring is 0 because it's at equilibrium. Now when it is compressed due to this spring at xm, the potential energy would be half k xm square, and the kinetic energy is of the mass is 0 because it has come to rest. This point 0. So the total energy again is half k xm square. This means that half k xm square is equal to half m v square. So kinetic energy, let me write one more here for you. Let me write this in. So this is before collision, this is after collision. Thus the total energy is conserved. Let us see an example. A block of mass 0.5 kilogram slides down a smooth curved surface and falls through a vertical height of 2.5 meter to reach a horizontal surface v. So it slides like this and comes here. Height is 2.5 meter. On the basis of conservation of energy, calculate the energy of the block at position A and speed of the block at point B. So initially at this point, this block has a potential energy equal to mgh, and the kinetic energy is 0. And at this point, the kinetic energy will be there, potential energy will be 0. So kinetic energy will be half m v square. So let's calculate the potential energy at A. mgh. What is m? 0.5. G 9.8. H 2.9. This will come around 12.25 joules. Kinetic energy is 0. So total energy at A is equal to, this will be the total energy at A, 12.25. At this point, potential energy is 0. So the total energy of the block at A will be the same as total energy at B. So total energy at B should be 12.25 joules. So half mv square should be equal to 12.25 joules. Therefore v square is equal to 2 into 12.25 divided by 0.549. So v is equal to 7 meter per second. This is the speed of the block at B. There is one more concept we have to see, is conservative and non-conservative forces. Conservative force has a property that the work done by them is independent of the path. Some of the examples are gravitational force, elastic force, and electrostatic force. The important thing is the work done by a conservative force on an object is 0 when the object moves around a closed path and returns back to its starting point. Let us see with an example here. See this figure A. So initially we say the work done is moving along the path A, path 1. Then another path 2, through this way also we can move. So here in conservative forces, work done by AB along 1 is equal to the along 2, that is independent of the path. Now in figure 2, if you see, it's the same two positions of the object, but one way it moves through this way and the other is returning back. Since it is equal, but the work done is opposite because the direction of force and distance is opposite. So work done would be negative from. Therefore, work done by AB along 1 is minus of work done BA along 2. That means we come to this conclusion. Thus, for the closed path, the conservative force is always 0. The other type of force we see is non-conservative force. In non-conservative force, the work done depends on the path. So if you see, force of friction is a good example for non-conservative force. Like say a block of mass m is moving on the surface at a speed v in the point V. After moving a certain distance along a straight line, the block stops at point P. The block has a kinetic energy of half mv square at A, and it has neither potential energy nor kinetic energy at point P. So it has come to a rest. There is a loss of energy. Where did it go? It has changed its form. So this is the work done due to the frictional force. And we can say that the force of friction was negative work because it's opposite in direction. So the kinetic energy is changed into thermal energy of the system. So the block with the same kinetic energy E is now taken from A to B, suppose say in another path 2. It may not even reach the point B. Before that itself it could have stopped. This obviously means the more work has to be done in this path. Thus we say this frictional force depends on the path. Last topic of this lesson is elastic and inelastic collision. Collision is like when two bodies interact, we term it as collision. And to note here, there is no external forces. Consider two balls. Say it is moving at velocity v1, this is moving at velocity v2. When it comes at this point in the surface, they just collide. This is a collision. Another example I can give you is a spring connected to a wooden block, compressed spring. See another compressed spring. If the equilibrium position of this spring is here, equilibrium position of this spring is here, they will collide. Like say so this will collide. This is purely due to the internal force of these two, or the restoration force. So this is a collision. We are going to do the two types of collision here. One more thing we have to note here is the colliding bodies move along the line, like in this case, and are joining at center. It's called head-on collision or central collision. There are two kinds of collision: perfectly elastic collision and perfectly inelastic collision. Like if the forces of interaction between the two bodies are conservative, it is said to be the total kinetic energy is conserved. Then the collision is said to be perfectly elastic collision. Here, total energy, kinetic energy before collision is same as the collision after collision. Such collisions are termed as completely elastic collision. The other type of collision is inelastic collision, where the colliding bodies stick together and move as a single unit. This is termed as inelastic collision. It's like a motion of a bullet embedded into the target. So, in elastic collisions, after the collision, so suppose this ball moves at velocity VAI and this moves at velocity VBI. before collision, after they collide, this moves with VAF and this moves with VBF. But in the case of inelastic collision, initially they were moving with velocity VAI, different velocity. After the collide, they move in this direction. Here, we have to know 2 points. The momentum is conserved in all types of collisions. What is momentum? M into V. And the kinetic energy is conserved only in elastic collisions. Momentum is conserved in all types of collision. Let us go into elastic collision, but to head-on collision in depth. Say initially the velocity of the two balls before collision be VAI and VBI, and after collision VAF and VBF. So initial and final are denoted using I and F. Now from momentum is conserved, so MAVAI plus MAVBI will be equal to MAVAF plus MBVBF. And for elastic collision, kinetic energy is also conserved. Elastic collision, half MVAI square plus half MBVBI square should be equal to half MAVAF square plus half MBVBF square. These are the things we get from conservation of momentum. If you observe here, there are two unknown quantities here, VAF and VBF. We have two equations. So if you solve these two equations, we can find the velocity after collision. I've left out the derivation part. So you can try out solving those two equations, substituting for VAF in terms of VBF. We can calculate VBF and VAF. Now let's go on to discuss some special cases. Now, suppose the two balls are identical, that is MA equal to MB. So initially condition is identical, MA equal to MB is equal to M. So this will be M. This will be 2M. So it will be 2MVBI divided by 2M plus VAI. M minus M is 0. This is 0. So the whole part is 0. M to M cancels. So VAF is equal to VBI. Similarly, this component will be 0. So it will be, this is 2M. This will also become 2M. So VBF is equal to minus VAI. So this is what we concluded here. VAF is equal to VB. That means that if there are two balls, this was VAI, this was VBI initially with the velocity there. So after colliding, the velocity gets exchanged. So VBF will be equal to VAI and VBI will become the final velocity of bowling. So the velocities are interchanged after collision. Let's move on to second condition. In the first condition, so we suppose if one of the ball is at rest, both the balls are identical. See, this is at rest. VB initial is 0. But this moves after collision. It is exchanged in, if we see for the identical cases, right? So after collision, this will move and this will be rest. So after collision, A comes to rest and B moves with the velocity of A. So the complete loss of kinetic energy or partial loss of kinetic energy by A is the same as the gain in the kinetic energy of B. Another special case we will see is, let's suppose the mass of the ball B is larger than that of A and particle B is initially at rest, then VBI is 0. So how do we come to that conclusion? Let's go back to this equation. The second condition was MB greater than MA, it's very large, and second ball is at rest. So here we can neglect the mass A and compare it to mass B. Then we can find that So in this case, this component will be 0. We can ignore this component, we can ignore this component, so it will become minus PAI. And if you see this part, PBI is 0, so this component is 0. And we can ignore this part, we can ignore this part. So basically 1 by something big will become 0. So approximately it's 0. This was a small ball, this was a big ball, this was at rest. So this was moving. It will move, and after collision, this ball remains the same. Ball B. Ball A, after collision, it moves again in opposite direction. That's why the minus sign. This will continue to stay at rest. So this is what we got. So after collision, the heavy particle continues to be at rest while the light particles return back on its path with the velocity equal to initial weight. This is what happens when a child hits a wall with a ball. These results find applications in physics of atoms, as for example in case in alpha particle with a heavy nucleus. We'll be learning these in the lesson atoms and nucleus. So this is the end of the chapter, work, power, energy. We have covered all the topics without missing anything from this chapter and have completed it in short duration. I hope this video is helpful to you. If you enjoyed this video, don't forget to like, share and subscribe. See you in the next video.